Okay, in this video we are going to look at an idea of what is called a cut edge. Okay, and cut edge, it is also called a bridge in a graph. Okay, so we are going to discuss cut edges or bridges in a graph. Okay, so let's consider this particular example. Let G be this graph. Okay, and here we can see that, okay, here I labeled the vertices by these red letters, okay, and edges by E1, E2, etc. So here we can see that if you look at these edges, okay, some of the edges have a particular property. Okay, for example, let's concentrate on this particular edge E5. Okay, so here we can see that if we delete this edge, okay, so if we delete E5 from this graph, okay, we can see that the graph will become disconnected. So we can see that when you delete E5, so that is G minus E, so we get this graph. So deleting an edge means, okay, you just delete this edge. So we can see that these vertices will stay, only the edge will get deleted. Okay, so here we can see that if you delete this edge, that is G minus E5, okay, we get this graph. And again we can see that, so if you delete that edge, the graph will become disconnected. And here we have two components, and one component contains this subgraph A, B, C, D, and the other component, it will contain this subgraph. Okay, and here the labels are E, F, G, H, I. Okay, so this kind of edges are what are called cut edges. So if you remove that particular edge, then the graph will become disconnected. Okay, similarly here again we can see that if you delete this edge, okay, if you delete this edge E9, okay, that is G minus E9, okay, again we can see that the graph, okay, G will get disconnected. Okay, so it will have one component. So if you delete this edge, you can see that, okay, the graph will get disconnected, and we have two components. So one component will contain all okay, this subgraph, and another component will contain, okay, this subgraph. Okay, and similarly you can also see that if you delete E10, okay, the same kind of thing holds. Okay, so here again we can see that, okay, this E9 and E10, okay, they are also cut edges. Okay, whereas, okay, we can see that if you delete any other edge, for example, if you delete E1, okay, we can see that the graph is still connected. And similarly with E2, E3, E4, E8, E6, E7. Okay, so those edges are not cut edges. If you delete that that edge, for example E7 in this case, or maybe E1, we can see that the graph is still connected. So they are not cut edges. Okay, so cut edges are edges that have this particular property, that if you delete that edge, the graph will become disconnected. Okay, and here again we can see that if you delete a particular edge, for example, if we look into this thing, okay, G minus E5, we can see that the number of components in G minus E5, okay, that will be equal to the number of connected components in G plus 1. So okay, deleting an edge, deleting a cut edge will only increase the number of connected components by 1. Okay, whereas if you consider a cut vertex, for example, so that may not be the case. So for example, if you let's consider this particular graph. In this case we can see that if you delete this particular edge, okay, we have, so let me label this thing like E, F. So if we this F is a cut vertex, so if we delete this cut vertex from this graph, okay, we can see that we have many disconnected, we have a disconnected graph with many components. Okay, so in this case, after deleting this thing, we have 1, 2, 3, 4, 5 components. Okay, so that's the main difference between this cut vertices and cut edges. This are cut edges. Deleting a cut edge, it will only increase the number of connected components by 1, whereas deleting a cut edge may increase the number of components by more than 1. Okay, or maybe if you delete a particular edge, the graph will still be not cut edge, cut vertex, the graph could still be connected. Okay, we saw many examples when we discussed cut vertices. Okay, so this is what is called a cut edge. If you delete that edge, then the graph will become disconnected, and also the number of connected components will get increased by 1. Okay, so that's the idea behind this cut edges. Okay, so let me give the definition of a cut edge in a connected graph. Okay, then after that we will look at some properties of these cut edges. Okay, so here is the definition. So let G be a connected graph so an edge E element of the edge set of the graph G, okay, is called a cut edge if you delete that edge, okay, G minus E. Okay, if G minus E, if you delete that edge from graph, okay, results in a disconnected graph. Okay, so we can see that these edges E5, E9 and E10, they are cut edges. So if you delete E10, the graph is disconnected. Similarly, if you delete E9, the graph will get disconnected, and the same thing with E5. Okay, so that's the definition of what is called a cut set. If you delete that edge, the resultant graph is a disconnected graph. Okay, and as I said, we can see that in fact, okay, if E is a cut edge, okay, then the number of connected components in G minus C, okay, it will be equal to the number of connected components in the original graph G plus 1. So deleting a cut edge, it will only increase the number of connected components by 1. Okay, and again we can see that if you look into, okay, these graphs, okay, that particular property holds, right? So again you can see that if you delete this cut edge E9, okay, we started with a graph with one connected component. So if you delete this thing, we have two connected components, one this subgraph and another this subgraph. Similarly, if you delete E10, okay, again the same kind of thing. We started with a graph having a single component. So if you delete E10, we have this graph and this isolated vertex, okay, graph. So you can see that the number of connected components will get increased by 1 if you delete a cut edge. Okay, and moreover, okay, here we can see that the maximum number of cut edges, a graph with n vertices can have is n minus 1. Okay, for example, if you look into this Pn, okay, a path graph on n vertices. Okay, here we can see that each edge is a cut vertex. Okay, this is a cut vertex, this is a cut vertex. Okay, so if you look into this path graph, we can see that each edge corresponds to a cut vertex, and here we can see the number of cut vertices will be equal to n minus 1. Okay. Similarly, if you consider a tree, for example, so we know that a tree with n vertices, it has n minus 1 edges. Okay, so that's the one defining property of what is called a tree. Okay, for example, if you look into this particular tree, okay, here we can see that number of vertices is 1, 2, 3, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The number of the edges is 12. Okay, so here we can see that if we delete any edge, for example, if we delete this edge, we can see that, okay, we have a disconnected graph with two components. Okay, so that says every edge in a tree is a cut edge. Okay, so this is also another example where this maximum occurs. The maximum number of cut edges in a tree with n vertices is also n minus 1. Okay, so this is the maximum number of cut edge a particular graph with n vertices can have. Okay, that is going to be equal to n minus 1. Okay, and again we can see that, so if a graph has a cut edge, then a cut vertex will also, okay, if a graph has a cut vertex, then it do have at least one cut vertex also. Okay, so that says whenever cut edge exists in a graph, we can see that cut vertices, it also exists. Okay, so the reason is that because at least one vertex of a cut vertex is a, okay, at least one vertex of a cut edge is a cut vertex. Okay, let's look into, okay, let me write down what I said. Okay, whenever cut edge exists in a graph, cut vertices also exist because at least one vertex of a cut edge is a cut vertex. Again, we will prove a statement related to this thing in a future video. Okay, so this says whenever cut edge exists in a graph, then cut vertices do exist, and okay, at least one of those, okay, one vertex of those cut edge is going to be a cut vertex. Okay, so if you look into this particular example for it, okay, so if you look here, we can see that, okay, this is a cut edge. Okay, so here it happened to be something like that. Okay, both the endpoints. Okay, here if you delete this vertex B, okay, we can see that the graph will get disconnected. Okay, so it will disconnected something like this. So B is a cut vertex. Similarly, E is also a cut vertex. Okay, and here if you look into this particular cut vertex, again we can see that the same kind of thing holds. Okay, so whereas if you look into this particular cut vertex, we can see that, okay, both the end vertices are not okay, if you look into this cut edge, we can see that, okay, both the end vertices are not cut vertices. Okay, only this one is a cut vertex. Okay, but here we can see that if you look into any cut edge in a graph, okay, we can see that cut vertices do exist, and at least one of the vertex of the cut edge is a cut vertex. Okay, so similarly you can also see that from these graphs. Okay, if we look into any graph, okay, any cut edge here, okay, we can see that if you delete this vertex, the graph will become disconnected. Okay, again with this thing the same true, and again you can see that the same thing holds for the path graphs also. Okay, so all the internal vertices are cut vertices. Okay, so that says whenever cut edge exists, cut vertices also exist in the graph. The other way that may or may not be true. Okay, for example, it says something like this: if a cut vertex exists, okay, so if a cut vertex exists, then a cut edge may or may not exist in the graph. Okay, a cut edge may or may not exist in a graph. Okay, for example, okay, let me give an example for such a situation. Okay, let's consider, for example, okay, this graph. Okay, so let's consider this particular graph. Okay, so in this case we can see that this graph, it has only a single cut vertex. So okay, this is a cut vertex. Okay, so if we delete that, the graph will become disconnected. Okay, that's why it is called, it is a cut vertex in this graph. So again, we can see that if you look into this particular graph, it has no cut edges. Okay, so one example is this particular thing. Okay, so okay, these two things says, okay, whenever a cut edge exists, then definitely a cut vertex do exist, and that cut vertex, it is going to be at least one of the cut vertices of that cut edge. Okay, and similarly, okay, if a particular graph has a cut vertex, then okay, the graph may or may not have a cut edge. Okay, one example is this particular thing. Okay, and okay, let's consider this particular graph G and this edge E which connects U and V. Okay, so here if you look into this particular thing, you can also see one important thing. Okay, so if you delete this particular edge, okay, let this be the graph G, and let's look into this graph G minus E. So if you delete this edge, okay, that's a cut edge anyway, so the graph will become disconnected, and we have these two components. Okay, one component consists of these edges, okay, these vertices and edges, and another component consists of this particular thing. Okay, so if you look into this particular thing, we can see that after deleting this cut edge, okay, one endpoint, so here we are considering this edge UV. Okay, so here U will be this vertex and V will be this vertex. Okay, and here you can see that this graph G minus E, it has two components, and one endpoint will go to the one connected component, and another endpoint will go to the other connected component. Okay, so that says if E equal to UV is a cut edge, okay, if and only if, okay, U and V, okay, U and V are in different components, okay, U and V are in different components in G minus E. Okay, so that's one other thing to be noted here. Okay, so if you delete a cut vertex, we can see that okay, both the endpoints will go to different connected components. Okay, and similarly you can also see one important thing here. So E is a cut edge, similarly this is also a cut edge, whereas if you look into these edges do not form a cut edge. Okay, so that says okay, these edges which are not cut edges, okay, they belong to a particular cycle. Okay, so that says okay, any cut edge, it doesn't belongs to any cycle. Okay, anyway, we will prove a statement related to this. Okay, this statement, any cut edge doesn't belong to any cycle in a future video. Okay, so that's one important thing to note here. Okay. And similarly, we can see that, okay, if you look into this particular graph, again the same kind of situation. Okay, here we can see that this E is a, okay, this E is a cut edge. Okay, UV, this E is a cut edge. So here suppose that we are going to remove this edge E, okay, that is G minus E. Okay, we get, since it is a cut edge, we get a disconnected graph, and here we have these two components. Okay, this one U and this one B. Okay, so here what we did is we took this graph and we removed this one. Okay, suppose that we are going to remove this vertex U. So let's see what is going to happen. So here we can see that, okay, this U is a cut vertex. So if we remove that vertex, then the graph will become disconnected. Okay, so U is a cut vertex, V is not a cut vertex. Similarly, these two are not cut vertices. So if we remove this U, okay, we get, okay, this graph. We are removing this thing, so we get this thing B. Okay, so if you look into this particular graph, we can see that, okay, whenever we have a cut vertex, cut edge, and the degree of the end points is greater than or equal to 2, okay, then that U is going to be a cut vertex. Okay, so here let me write down what I said. Okay, whenever, okay, E equal to UV is a cut edge, okay, something similar to this thing, and okay, degree of U greater than or equal to 2, okay, then, okay, that U is also a cut vertex. Okay, so here we can see that this V is not a cut vertex because it doesn't satisfy this condition. Okay, whereas this vertex U, okay, which is an end point of this edge, which is a cut edge, and the degree is greater than 2. So degree of U is 3 here, right? Okay, so okay, that says that vertex will be a cut vertex. Okay, so let's look into the first example here. So here again we can see that, okay, these two vertices are cut vertices, and E5 is a cut edge. We can see that the degree of B is greater than or equal to 2, degree of E is also greater than or equal to 2. Okay, so that says this will be a cut vertex and this will be a cut vertex. Similarly, if you look into this particular edge E9, okay, these two vertices F and H are also cut vertices. Okay, E9 is a cut edge and the end vertices are F and H, and the degree of F is greater than or equal to 2 and H is also greater than or equal to 2. So that says F and G. So sorry, F and H is also, they are also cut, because these vertices F and H, they are cut vertices as well. Okay, so another case, if you look into this particular thing, E at number 10, okay, here we can see that, okay, this endpoint, it has degree 2 whereas I has degree 1. Okay, so that says, okay, this H is also a cut vertex. Okay, similarly you can also see that kind of thing here. So if you remove this, okay, this is a cut edge anyway. If you remove that, the graph will become disconnected, and here the end vertices are E and F. So degree of E is 1, so that says, okay, E is not a cut vertex. Okay, degree of F is greater than or equal to 2, so that says F is a cut vertex. Okay, so anyway we will prove that statement in a future video. Okay, so that says whenever E equal to UV is a cut edge and degree of U greater than 2, then U is a cut vertex. Okay, so that's another thing to node. And one more thing, so here we can see that this is K2. So here we can see that, okay, this edge, if it is a cut edge, okay, if you remove that one, okay, you get this disconnected graph, these two isolated vertices. Okay, and again we can see that, okay, these two vertices, they are not cut vertices. Okay, and this is the only connected graph that has a cut edge but no cut vertices. Okay, so this is the only connected graph, okay, that has a cut edge but no cut vertex. Okay, so in the next few videos we will see some characterization of cut edges and, okay, the proof of for these statements that we noted here.